Okay, so out of many error correction schemes, uh, we looked at something called error detection techniques, error correction and detection using cyclic redundancy, CRC. But in cyclic redundancy, in CRC, what happens that you can only detect error. Now, what about if I want to correct that error? When I use CRC, we detect an error and then we ask the transmitter to retransmit that. But there are also sophisticated codes, like for example, you can say, which are known as forward error correction codes, FEC, for forward error correction codes. Forward error correction codes, which does not only detect error, but they can also correct the error at the receiving end. They are very sophisticated codes, so they are known as forward error correction. And one of the most basic code in forward error correction codes are known as Hamming codes. So one of the most important error correction codes are Hamming codes. So let's do an example of this. I don't want to, let's do an example and let's see how does these codes work. So the first step we need to do, we need to remember this. When I'm doing forward error correction codes, especially Hamming codes, the first criteria is that, let's say, so this is the criteria that I need to meet. So the criteria that I need to meet, so what I'll be doing is this. I'll have data bits that I'm transmitting, and I'm going to add some bits to it, which are going to be called Hamming bits. Uh, and then these Hamming bits will let me know if I have an error. If I do have an error, how do I actually correct that error at the receiving end without asking the sender to resend the data again. So the first thing I need to do is this. So the first criteria that I need to meet is I need to do is the criteria is 2 to the n greater than or equal to m plus n plus 1. This is the criteria I need to meet. What is that criteria that is saying? Where m is number of, where m is your number of data bits, n is number of Hamming bits that we need to add in our data. All right, so m is number of data bits, n is number of Hamming bits. These are the bits that I need to add in my data. Okay, so let's say if I have, so first, for the sake of our example, let's say here I have 8-bit of data. All right, so let's say I have 8-bit of data. In that 8-bit of data, okay, so I have 8-bit of data. Let's say my data stream is something like 100110001. So I have 4 bits here and I have 4 bits here. This is a 4-bit of data. How many Hamming bits do I need to add? Now the question is, how many Hamming bits do I need to add? So this is the criteria I need to fulfill. So for example, if I were to add 2 Hamming bits, all right, so what is 2 raised to 2? Is 4 plus m plus n plus 1. So are these bits greater than the addition of these bits? So how many of data bits I have is 8. How many am I going to add Hamming bits? 2 plus 1. So this is 8 plus 2 is 10 and plus 1. So no, it's not fulfilling the criteria. This number is not greater than this. So we need to try 2 raised to 3, which is 8. Surely it will not work out. If I try 2 raised to 4 bits, that is definitely going, this is going to be 16. Then 8 plus 2 plus 1, this is definitely going to be greater than this. So I need to add how many bits of Hamming bits in our example? 4 Hamming bits I need to add. So I need to add 4 Hamming bits in order for me to do the error detection. At the same time, I need to do error correction. So I need to add 4 bits. Okay, the way I'm going to do it is this. So the first thing I'm going to write my bit positions. All right, so I'm going to write my bit position. And so I need, with 8 bits, I need to transmit 4 additional bits. So the total bits that I'll be transmitting with Hamming bits are going to be 12 bits. So 8 bit of data, 4 bit of Hamming bits. This is what I need to transmit in order for me to perform error correction and detection. So what I'm going to do, I'm going to take this and I'm going to write bit positions. So I'm going to say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are going to be my bit position. All right. So I'm going to randomly place my bits starting from least significant bit all the way up to most significant bit. All right. So I'm going to place it from my right all the way all the way up to left, where least significant will be in position 1 or however we want. Okay, so what we're going to do is this. We're going to randomly place 4 Hamming bits. We don't know what bits are going to be there. What would be the bit sequence? So we're going to randomly place. So let's say at bit position 1, we're going to place our least significant bit, which is 1. And then in this place, I'm going to place an Hamming bit. I think this is not a right color. Let's try purple. So H for Hamming bits. So 1, H, this is where I place my Hamming bit. I'm going to place 2 zeros here. All right, then I'm going to place a Hamming bit randomly. I'm placing Hamming bits. Then my bit 4, I'm just going to place it here. I'm going to put bit 7 here. Then I have one Hamming bit here. Then I have 2 zeros. So 1 0 Hamming bit, and then I have 0 and I have 1. So this H is representing what? My Hamming bit. Hamming bit. I don't know. I haven't calculated yet what are going to be those bits, but I'm just randomly placing them. So here's my data. That is 1 0 0 1 1 0 0 1, and I have randomly placed Hamming bits. So now what I'm going to do, I'm going to calculate Hamming bits. So the next step I'm going to do, I'm going to compute. So the next step is, second step is going to be, I'm going to compute Hamming bits. All right, the way I'm going to do it, I'm going to take those, the way I'm going to compute Hamming bits, the way I'm going to do it is this. I'm going to take the bit position where I have 1. All right, so I'm going to take the bit position where I have 1. So where do I have my 1? First occurrence of 1. This is in bit position 1. So I'm going to write bit position 1, and I'll convert that bit into 4 bits. Okay, so what is the representation of 1 in binary? Is going to be 0 0 0 1. So bit position 1 is going to be 0 0 0 1. All right, where does the second bit occur? That is at second one occurs. That's at bit position 6. So bit position 6. And how do I, when I convert that into binary, this is going to be 0 1 1 0. Okay, so this is that. Then I'm going to perform XOR. So in XOR, when I perform XOR, when I have 2 different things, I'll get 1. So I'll get 1 here, I'll get 1 here. When I have 2 same things, I'll get 0. So basically you're doing modulo 2 arithmetic. So next position that I have where I have 1 is actually bit position 7. So bit position 7, and 7 in binary is going to be 0, 4 plus 2, 6 plus 1, 7, and I'm going to perform XOR. So once I perform XOR, everything is same. I'll get 0, 0, 0, 0. Where do I have 1? I have 1, so at bit position 12. So bit position 12 is 12. So 12 in binary is 8 plus 4 is 12. So it's going to be 1 and 1, 0, 0. When I perform an XOR sum, so this is going to be 0. This is going to be 0 because they are same. These are different. So I'll get 1. I'll get 1. So these are going to be my Hamming bits that I need to add in place of this H. All right. In place of this H, these are the bits that I'm going to add, starting from the most significant bit on my right and going all the way up to least significant bit on my right, all the way up to most significant bit on my left. So these are the Hamming bits I'm going to add. Okay, so now this new data would turn out to be, so my Hamming bits is 0, 0, 0, 1, 1. So the new data, it will turn out to be 1. Then I'm going to take this Hamming bit right here. I'm going to take this Hamming bit, which is 0. I'm going to place it right here. Then 0, then 0. All right. Then Hamming bit has to be 0. Then 1, then 1. Hamming bit is 1. So 1, 0, 1. These are the two ones that I just added. Then 0 and then 1. All right. So these are the Hamming bits. I'm going to just simply highlight them for you. So these are the Hamming bits which I just added. These are the Hamming bits which I just added. All right. So after adding these Hamming bits, I'm going to transmit this data. What my receiver will do, transmitter will do, it will transmit this data. Okay, receiver will also have a knowledge of what are going to be those Hamming bits, so they're going to treat them as an Hamming bits. So receiver would know what are these Hamming bits. So let's say, so during transmission process, during transmission, let's say error has occurred. Error has occurred. And this error has occurred at bit position, let's say this error had occurred at bit position 6. All right. So error bit 6, bit position 6. During that transmission, error has occurred as bit position 6. So instead of receiving 1, I get 0. All right. I hope you're getting it. So during the transmission, what happened? You send this data that you have sent, this and this. This data that you have sent, and during that transmission, bit has error bit number 6 got corrupted, and instead of 1, you got 0. So receiver, what does the receiver will do? This is the task that receiver needs to perform. What receiver will do? So receiver task. All right, it will take those Hamming bits. So you will take those Hamming bits. So Hamming bits. So Hamming bits, it will take 1, 1, 0, 0, and it will see where does 1 has occurred. All right. So this is what we have transmitted. And during the transmission, bit number 6 got corrupted, and instead of getting 1, we got 0. So what receiver will do? It will take those Hamming bits and it will do the same thing that we have done to generate Hamming bits. Wherever the one has occurred in whichever position, it's going to take that position and it's going to XOR these two values. So let's say, okay, the first one occur at bit position 1. So bit position 1, number 1. So 1 in binary is going to be 0 0 0 1, and it's going to perform XOR. All right, so once you do XOR, you'll get 1 0 1 1. Okay, then it's going to check and see where does 1 has occurred beside those Hamming bits. So in actual transmission this was 1, but during the transmission, due to an error, this has become 0. So the next one is in bit position 7. So bit position number 7. So 7 in binary is going to be 4 plus 2 plus 1. So this is going to be 0. So I'm going to do XOR again. So this is going to be 0, this is going to be 1, this is going to be 0, this is going to be 1. All right, where does this 1 has occurred? In bit position number 12, beside those Hamming bits. So bit position 12, position 12. All right, so bit position 12. So what is 12? So 8 plus 4 is 12. So these two are going to be 0. So this is an XOR. We're going to do XOR again. So I'll get what? 0 1 1 and 0. So this is the location where bit error has occurred. A single bit error has occurred. So if I convert that into decimal place, this would be what? What is 4 plus 2? It is actually bit position number 6. And this is where the error has occurred. So the receiver will look at bit number 6 and it will see, I am receiving 0. It's mean, what is the other, what is the opposite of 0? Because we're transmitting in binary. The other thing is going to be just 1. So it's going to flip this bit from 0 to 1. I hope you got this. So once the receiver performs this task, the last XOR summation would give me the location of bit, that bit position where we have a when we introduce our error. This was at bit position 6. So at bit position 6, it will, okay, see, I'm getting 0 here, but I was supposed to get 1. So receiver will automatically correct that by taking 1's complement. By adding 1 to it, it will automatically correct this 0 to 1. And in this way, you don't need to ask the receiver to send this data again, to retransmit that data again. And this is how Hamming codes work. Okay, you gotta remember this, that this is only if there is an error in Hamming bits. It won't be able to correct that error. Plus the example that we have done is for single bit error. All right, so yes, there are different variation of these Hamming codes which are available, of course, but we're looking at the basic example of Hamming codes. How does these forward error correction codes work, where you can actually detect an error, at the same time correct it without asking the transmitter to retransmit that data again. Yes, if you want to correct more than 1 bit error, then you gotta add more bits to it. So basically, the higher the number of data is going to be, you gotta add more and more bits to it, and that's how you do error correction and detection. So I hope you like the video.